Often, mathematical formula require the addition of many variables. Summation of sigma notation is a convenient and simple form of shorthand used to give a concise expression for a sum of the values of a variable. Welcome to Mathematics of Engineering. The simple definition of summation notation is a concise way of representing the terms in a series. Summation notation is also called sigma notation, denoted by the Greek letter sigma. It is with the same principle of using S when computing the summation of terms in a sequence. S is for sigma. With the Greek letter is the index of summation I, but other variables are also used like k, j, and so on. Below sigma shows the lower limit or the initial index, and that above is the last index or the upper limit. For the series presented, a simpler expression would be using the sigma notation where the initial index starts with 1 and ends with 5, and the expression will be of the same value as I. Computing the summation of the terms will be 15. If the next series has the pattern of taking the square of an increasing index, the sigma notation will have the expression of I squared with the initial index of 1 and final index of 6. Solving for the sum yields 91. Let's move on to some more examples. Evaluate the following notations. The sigma of n cubed with n equal to 1 until 5. Expanding the notation will require the substitution of n into the terms giving 1 cube, 2 cube, 3 cube, and so on until 5, the final index. Take the total of the terms, which gives 225. In case the example is the sigma of 3n, where n is from 1 to 5. In such an example, the varying part of the term is its exponent with a base of 3. Thus, the expanded form reflects 3 raised to 1 plus 3 raised to 2 until 3 raised to 5, and so the summation is 363. Now, what if the initial index is 0 instead of 1? Many students overlook the fact that the number raised by 0 is 0 while it is supposed to be 1. And all the other procedures for the example will be similar with the previous examples, where the expression will give a summation of 63. With a more complicated expression, simply plug in the values of the indices to be able to arrive at the proper expansion and answer, and with sigma of half of r multiplied by r plus 1, our sum would turn out as 20. In cases where infinite series are observed, the sigma notation will keep n for its final index. In the example, the sigma of 2 raised to k, where k starts to 1 but is infinite, the expansion will become 2 raised to 1, 2 raised to 2, until 2 raised to n. The summation will be undetermined. In case the series is provided and you are required to write the notation, take, for example, the series provided starting with -1 until +1 of 100. In this example, the first term -1 can also be written as a fraction -1 of 1, so the series can be written as shows. We also notice that the signs of the terms alternate with a minus sign for the odd-numbered terms and a plus sign for the even-numbered terms. So we can take care of the sign by using -1 raised to I, which is -1 when I is odd and +1 when I is even. We can therefore write the sum as shown. We can now see the ith term is -1 raised to I times 1 all over I, and that there are 100 terms, so we would write down the sum in sigma notation as shown. In order to write a number in sigma notation, try to find a formula involving a variable I where the first term can be obtained by setting I equal to 1, the second term by I equal to 2, and so on. Take this other example where the series starts with 9 and terms decrease in a specific pattern. As noted earlier, the index should primarily start with 1, and counting the terms, the final index is 6. Next, check the pattern between the terms. There is a gap of decreasing 3 with each jump, so the sigma notation may have negative 3i. Now, unlike the other series where the first terms are those nearest to 1, this example shows a bigger initial value, so with negative 3i, check for a value to reach 9, and that is adding 12. By checking at the initial index, negative 3i is negative 3 times 1 plus 12, which is 9, and at I equal to 2, negative 3i plus 12 is 6, so we arrived at the right notation. Sigma notation is a recursive method, which means that the procedure needs to expand the series first before arriving at the final summation of terms. However, there are formulas for some special series which only consider the last index. First is the sum of n ones, where sigma 1 will just be n. Imagine adding 1, n times will still be n. The second formula states that the sum of the positive integers from 1 to n is half of n times n plus 1. The last formula for special series states that the sum of the squares of the positive integers from 1 to n will be taken as the sixth of n times n plus 1 and 2n plus 1. Let's evaluate the notation for the square of I until the 10th term or the nth term where I starts with 1. Expanding the notation will be like saying 1 squared plus 2 squared and so on until 10 squared. But needless to complete the expanded form of the notation, use the special formula which can simply give you 6 of 10 times 11 times 21, or that would be 385.